This video is part of a series of presentations covering the key concepts of multithreading and synchronization. This specific presentation covers details of data parallel applications or synchronization-free multithreaded programs that are widely used for multithreading many applications. Many problems and algorithms lend themselves to synchronization-free multithreading. Keep in mind that these problems do not require or need any use of semaphores, mutexes, or any other synchronization primitives because these applications are designed such that they do not share any memory locations. Multithreading programs such as these decrease the overall runtime, but not the time complexity of algorithms, but the overall runtime by utilizing multiple cores or CPUs available on a single computer. Synchronization-free approaches are the fastest or the best approaches for multithreading. This is because synchronization essentially forces parts of the program to run in single-threaded mode, which then decreases overall performance of the program. Consequently, we try and strive our best to develop synchronization-free multithreaded programs because one, they are easier to develop, and two, they provide the best possible performance with multi-threaded solutions. There are two categories of synchronization-free multi-threaded programs that we'll be covering in this presentation. First, we'll look at data parallel multi-threaded programs where each thread runs the same method or algorithm but operates on different input data to generate different output data. So here, each thread will operate on different inputs. So here inputs are D1, D2, D3, a list of inputs. Every thread runs exactly the same method or algorithm to generate corresponding output for each one of the inputs. The second category of multi-threaded synchronization-free programs are called task parallel programs, where each thread essentially runs a different algorithm, but every thread operates on the same input data, but it's a read-only input data and generates different outputs, independent outputs for each one of these threads. So the difference between data parallel is every thread runs the same algorithm and has but with different input data. With the task parallel, every thread operates on the same input but runs different algorithms. Keep in mind, data parallel programs do not require any synchronization, so that means we'll have to design our programs with that in mind. And there are many applications that fall into this category. So for example, a lot of the image processing applications fall into this category where an image is subdivided into regions and threads operate independently on the regions or pixels in that region and update the image. And a lot of the image processing applications operate this way. Similarly, there are many file processing applications where you can have a large number of files and different threads can work on different subset of files independently without requiring any synchronization. Keep in mind here, each thread must update or work with independent memory locations in order to avoid race conditions. But sharing read-only data or constant data is not an issue between different threads. So here constant is your friend. So if you're not planning to modify some variables or data, ensure they're all tagged constant so it is clear that that information can be safely shared between multiple threads. Data parallel or synchronization-free programs are ones where threads do not update or work with shared memory resources. So the analogy to this is cars operating on their own lanes, where lanes are like memories and cars are like threads. And as long as they operate on their own independent lanes, you can develop synchronization-free programs because they all work on independent subset of memory or variables. So here, for example, you can have a list of input values in a vector. Each thread can operate on an independent input and generate independent outputs. And here, each thread works on a pre-allocated list of values, and they do not modify, add or erase entries from the list, but only modify or update their respective outputs. And these types of programs do not require any synchronization and are essentially data parallel applications. There are a couple of different data parallel applications. One is one-to-one data parallel application where each thread operates on one or more inputs, and for each input it generates a corresponding output. So for example, you have a list of inputs. Each threads can operate on a corresponding set of inputs for them, and for each input the thread generates a corresponding output. Notice here threads are operating on a subset of inputs. So for example, you can have millions of inputs and a few threads, and the few threads operate on millions of inputs by working in blocks of consecutive inputs so that they can all be processed. Another type of data parallel programs are one where there are many inputs from which a single output is generated, and these are called reductions. Each thread operates on one or more input-output pairs. Of course, each thread has an independent subset of data to operate on. And each thread first generates its own local intermediate result, and then the main thread computes the overall result. So for example, here, let's say you have millions of inputs. We have a few threads that are operating on those inputs. So each thread works on a block or a set of inputs. They all operate on it and generate an intermediate output. So here, for example, you might have millions of numbers that are then reduced to a few intermediate results. And then the main thread, once the threads finish, the main thread operate on the intermediate outputs to compute the overall result. So these are the two types of data parallel applications that we'll be covering in this presentation. First, let's start with a serial program before we get into the data parallel examples. Assume that you're given a method called prime check that you need to multi-thread. So prime check is going to operate on a list of numbers and count some factors associated with each number. So here it's going to create the results that it needs to compute, and then it's going to iterate over each number in the list and compute the factors for each one of those numbers and stores it into the corresponding location and results. A pretty straightforward serial program that we want to multi-thread. Notice that here, for each input in the list, we are generating or computing a corresponding output and storing it in the results array. So for example, given a list of input numbers, we want to generate a corresponding set of results in the output vector. And each thread is going to operate on a subset of numbers, but an independent subset. That means no two threads is ever going to operate on the same set of numbers. That is since they don't operate in the same set of numbers, we don't need any synchronization in this example. And this is an excellent example of a data parallel application. Now let's look at how the source code for such an application will be set up. So we'll have a standard pound includes. We'll have a helper method that will help us to do factor counting. And then we are going to have some shortcuts to refer to vectors of longs and integers. Here is our thread main method, which is going to take an input list of numbers that it needs to process, an output list of numbers and results, and the starting and ending index in the list. The same corresponding entries apply to result vector as well. So it's going to iterate over start and end index to compute the results. Keep in mind this method is going to run on different threads, and each thread will have its own starting and ending index that it's going to iterate on. So you should visualize this as a list of values. So that means the num list contains a long list of values. Each thread is going to work on a subset of numbers. The start and end index is going to indicate the subset of numbers a thread should work on. So in the for loop, the thread starts at the first entry, iterates over each entry, and computes output. So you should be able to visualize this where each thread starts at a given starting and ending index is going to start at an entry and compute the output values. So this is how this method is going to be set up. Now let's see how to call this thread main method to accomplish the multi-threaded task. So we're going to have a prime check program that takes an input list of numbers and needs to compute the results. We're going to assume in this example you're going to work with 3 threads, but it could be any number of threads. So here we're going to create an intermediate variable called list size just to keep the source code readable. And then here we are going to compute the number of inputs or values each thread is going to work on by dividing the list size by the number of threads. Then we are going to create the threads we want to operate. So we're going to iterate on the start and ending index based on the number of threads. We're going to keep track of the ending index for each thread. We'll compute the ending index such that the end index never goes beyond the maximum number of values we have in the list. And then we're going to create the thread. Notice that we are using studRef to pass references. So that means all the threads share the same vector. However, they work on subset of entries in the vectors and they do not add or erase values in this vector. So they're only updating values in this vector. Hence, it is safe for them to share those vectors and update the values. Once the threads are spun up, we then use a separate for loop to wait and join those threads. Notice the same two loop pattern. The first loop creates all of the threads, so all of the threads start running asynchronously in parallel, and a second loop waits for the threads to finish. So this is an example of a data parallel program that we took a simple serial example and parallelized it as a data parallel application. Now let's look at an example of reduction. Remember, reduction is where we have a large number of inputs and we want to reduce it to a single value. Examples would include lots of statistical operations like sum, mean, mode, minimum, maximum, find operations, or search operations where we have a large list of numbers and we want to get to a single result. Here, reduction involves two major steps. First, we're going to have a given number of threads. These threads are going to generate some intermediate results. And then here's where the reduction happens, where a large number of inputs, say millions of inputs, are reduced to a few intermediate results concurrently by multiple threads. Then once the threads are finished, the main thread then collects the results. Now the main thread has only a few results to work, intermediate results to work with. Using those few intermediate results, it'll compute the overall result. Let's look at an example where we want to reduce or find the sum of 10 numbers using 3 threads. So given a list of numbers, we are going to have each thread compute the sum or a subset of numbers. So each thread works with its own independent subset of values and computes intermediate results by adding all of the numbers in their range. Once all of the threads are finished, that means they join, the main thread then has only 3 results from which it has to compute the final result of 15, which will be the total of all of these numbers. So it's a two-step operation. Now let's see how to implement this in a C++ program. So we have a standard set of pound includes. We're going to have a number, a vector that's going to contain all the numbers we want to sum. We're going to create our thread main method, which is going to get a list of numbers, and it's going to update the sum value that's given. And we're going to have a starting and ending index on which the thread needs to operate. Here we'll just use the std_accumulate algorithm from the numeric library to add all of the values from a given starting index to ending index. So you should be able to visualize this, that the list that is given to us has all of the values. Each thread gets a specific starting index and ending index, and it iterates over that list of numbers, adds them together, and generates the intermediate result in the sum parameter that is supplied as through a reference to this method. Now let's say how to call this thread main method. So we're going to create our sum method. Here again, we're going to, just for simplicity, assume we have 3 threads. Again, we are going to compute the number of inputs to process, evenly divide the number of inputs between the different threads. Then we're going to spin up our threads. Before we spin up, we're going to create intermediate storage locations for storing the results, the intermediate results from each thread. So we're going to iterate pretty standard for loop that's going to skip over the count number of entries for each thread. Again, compute the end so that we don't go past the size of the list that we have. And then create the thread. Notice that here we are passing the intermediate sum for each thread through reference. So each thread stores this intermediate result in a separate entry in that vector. Then we wait for the threads to finish. So we wait for the threads to join. Now finally the main thread, again here notice the 2 loop pattern. And then finally the main thread again uses the std_accumulate to add up all of the intermediate sums to generate the overall total. So here we are first reducing all of the results into a few intermediate results, and then the main thread has to work only with a few numbers to calculate the final result. And this is another strategy called reduction that is used for in data parallel programs. Now that we have seen couple of examples of data parallel programs, now let's take a brief look at task parallel programs. Recollect that in a task parallel program, there is one input data and multiple threads are running different methods or algorithms to generate different outputs. Here, we are going to try and use the std_async API method that streamlines the task of running these programs and getting results from these algorithms. So given some method f, the std_async method call runs that method f for us from a separate thread. Keep in mind, std_async will return quickly after starting the thread. So for example, when we call std_async with the function f, it immediately spins up a thread and returns what is called a future object, which can be used to obtain the return value from the method f that was called. Keep in mind, the future basically says that the results are not available right now because the thread is still running, but you will get the results in the future once the thread has completed running. Keep in mind here the thread runs asynchronously and the main function can continue with its operation. And then finally, we will call the get method on the future, which will then go get the result from the thread and give the result from calling that function from a separate thread. Keep in mind that the std_async method runs the given function asynchronously in a separate thread, and it returns a future class that is used to obtain the result. So let's look at it in a example. Notice the pound include of the future header. Now let's see how to call this game of life method from a separate thread using async. Notice that game of life returns an integer. In this case, it just returns 20. In the main function, we will want to get the result, but we'll get it in a future. Notice that the future is holding on to an integer because the return value of game of life is also int. So notice that the int usage here and the return value in game of life. Here we are launching the thread using the async method, and we want an asynchronous launch. That means we're telling it create a thread, call the function game of life, and we have to give it a parameter for the an argument for the parameter string s. So we're just giving the word async here, and then we could pretend to do some operation. We could be doing some other computation here, but in this example we're just sleeping for 5 seconds. And finally we get the result from the future by calling result.get. Notice that here result.get returns the result from calling game of life method. In this case, it'll return the value 20. So keep in mind, this launch async will run the method in a separate thread, and the result.get will wait until the thread has finished running. So if the thread is still running, this method will block and wait however long it takes for the thread to finish, and then returns the return value from the thread. If the thread is already done running, maybe a long time ago, you will immediately get the value from the return value from that thread. Of course, you can use many async calls for parallel multithreading. So for example, let's say you have this application where you're counting words in a file, and assume that this word counts on a given file is the one that is the most time consuming or taking the most time to do this operation. We can use std_async to multithread this program to make it run faster. So for here, we will create a method called count words in files. And we are going to notice that here we are going to create a vector of futures. That means we are going to get the result from these threads in the future. We are going to iterate over each one of these and use the std_async method to launch threads asynchronously. Each one of these std_async calls returns a future, and we are going to hold on to these futures so that we can go and inspect or interrogate these futures to get the results. Then once all the threads are spun up, we are going to go call the get method on these futures to get the word count of from each one of the files. That means each thread operates on a separate file and gives us the count of words in each file. And then we accumulate the results in this word count variable and return the word count. Again, notice the two loop pattern. First loop to launch the threads. Here we are, instead of explicitly creating threads, we are calling the async method. And then notice a separate loop to call get, which essentially calls join internally and obtains the return value from that method and stores it into the future. And this is a very typical operation, two loop pattern to manage with futures. All right, in this series so far, we've looked at introduction to threading and the basics of multi-threaded program and measuring the performance of multi-threaded programs. Then we looked at issues of race conditions. And in this presentation, we looked at how to develop data parallel applications that do not require synchronization. This is the first part. In the second part, we look at detached threads for certain kinds of applications. Then we look at synchronization for different kinds of programs. Hope you found this interesting presentation useful. And don't forget to check out the other presentations in this series.